Good morning. We have another Codeforces round today. This time it's an educational round. It's rated for Div 2. I am not Div 2, so it's not rated for me. But it should be fun to try nevertheless. Also, I wanted to let people know I will be at North American Championships starting tomorrow morning, Friday morning. So if you're going to be competing in the North American Championships, let me know. Say hi to me. I'll be there. I'd love to see you. And please make sure to submit your fun facts to a Codeforces blog that I will make soon. All right, let's jump in. We're like 3.5 minutes late, but that's not a problem. You're given two integers x and k. Grasshopper starts at point 0 on the x-axis. In one move, you can jump some integer distance that's not divisible by k. What's the smallest number of moves it takes you to reach point x? So if x is 1, you could be in trouble. Otherwise, you can always do 1 and then there. Oh, not divisible by k. Okay, so otherwise you might have to do, oh yeah, you can just do there or 1 there. Okay. So if x mod k is not equal to 0, out.println 1, out.println, do we just print the distances? You start at position 0, print x, else out.println 1, out.println 1 plus x minus 1. Here we go. This is 2. Okay, we'll just submit this here. Submit a, see if it's right. Let's open up the problems here. Please. Okay, B, C, D, E, and F. Take a look at B while it's judging. The samples for B are incorrect. They'll be fixed in a minute. All right, you're given a string S of length n where each character is left or right. An array of n plus 1 elements is compatible with a string if for every I from 1 to n, the character at Si represents the result of comparing AI and AI plus 1. Oh, okay. So, I see. All right. For example, this is compatible with this array. So you go, yeah, so less than, greater than, greater than. Yeah. The cost of an array is the number of different elements in it. You need to calculate the minimum cost among all arrays which are compatible with the given string S. Is the number of different characters? So this would be 3. Also 3. 6. Yeah, so they're just off by 1. Okay, let's do that. They're gonna have some big technical difficulties here if they're printing the wrong answers to samples, but we'll see. Int n equals this, char array line is fs next to char array. All right, so now we need to actually solve this. So how do you do it? It looks like it's just the deepest that it gets. Yeah, so int count equals 0, max equals 0, min equals 0. I think this is it. We're just going to leave that for a while and let it be. We have a string S consisting of 0, 1, and question mark. That's a pattern, okay? Let's say the binary string matches a pattern if you can replace question mark with 0 or 1 so that the strings become equal. For example, this matches this, yes, okay? But that one, okay, but 0, 1, 0 doesn't match 1, question mark, question mark, question mark, question mark, or this. All right, let's define the cost of a binary string as the minimum number of operations of the form reverse an arbitrary contiguous substring of the string. So how many range reversals do you need to sort the string in strictly non-descending order? So you want to sort the string. All right. We want to find a binary string with the minimum possible cost among those that match the given pattern. So you just make these all ones. Make these all zeros. Make these all zeros, make these all ones. It seems pretty easy, right? You just look at the things around this and you set it to that. Multiple answers, print any. Yeah, okay. So, ooh, we can just set it to the thing that's before it always. Yeah. Nice. Unless it's the first one. Okay. Yeah. I don't have any proof for that. That's just intuition, but I think it's right. Oh, we don't have n, we just have this. All right, fine. Char line, fs10 next, add to char. Char first equals 0 for char c in line. If c is not equal to a question mark, then first equals c. And break. And then for char, or for int I equals 0, I is less than line.length, I plus plus. If line I is a question mark, then set it to first, and then first, else first equals line at I. Looks good to me. Submit C. Running answer test 2. All right, that's problematic. Yeah. That's not right. So you can have, if you have, for B, if you've got greater, greater, less than, greater, you can do 5, or you can do what, 3, 2, 1, 3, 2, 1. So I'd get that wrong. 5. Try this. Could just be totally wrong though. All right, we got C. Let's try D. A bracket sequence, a regular bracket sequence, we know what this is. The bracket sequence is beautiful if one of the following conditions is satisfied. It's regular, or if the characters are, if they're reversed, it becomes regular. That doesn't just mean they have the same number of things. Yeah, so it means if you make a mountain, the mountain's either always above 0 and ends at 0, or always below 0 ends at 0. Color the given bracket sequence into the minimum number of colors. What? You have to color it so that every bracket's one color. For every color, there's at least one bracket colored by that color. For every color, if you write down the sequence having that color in the order they appear, you get a beautiful bracket sequence. Color into the minimum number of colors according to these constraints, or report that it is impossible. It's got to be possible with 2, right? Maybe not. Yeah, it's possible with 2, always. Yes, okay, so what if it's impossible if they don't match? If you have bad counts? 1, 2, 3, 4, yeah, okay. C, this is D. So we'll say int n equals this, char array line, next dot to char array. Then count plus plus, else count minus minus, and then if count's not equal to 0, out dot print line -1, continue. All right, so then we have to actually color it. All right, so int array colors equals new int array n. We can have Boolean was positive equals false, Boolean was negative equals false. And then we can say if counts greater than 0 was positive equals true. And then if it's less than 0 was negative, it's true. All right, and then if not was positive or not was negative, and we go 0, then we should be fine. So now we can just say out.println 1, and then for int I equals 0 less than n plus plus dot print 1 plus a space dot println. Continue. out dot print line 2. Int count equals 0. Oh yeah, I guess just count equals 0. Well, it should already be 0, so we're fine. So then for char c in line. So if old is not equal to 0, then I guess if c equals open parenthesis, then we'll say count plus plus, or count, yeah, count plus plus, else count minus minus. So if old is not equal to 0, then out dot print line, or out dot print, sorry, old is greater than 0. If so, 1, otherwise 2. Else, if count's greater than 0, out dot print line, count is greater than 0. If so, 1, otherwise 2. Plus a space. It should just be normal print. And then we need print line. It should be good. Oh. Print line. Why would we not have this here? Oh. Yeah, that's fine. Okay. We got B wrong again. Dang it. All right. Let's think about B here. Well, did we actually test this case? 3. I think that's right, actually. Ah. Well, no, that's fine. Yeah, why is this wrong? Is it just the most matching things in a row minus 1? Is that not what I'm doing? It's just a roundabout way of doing that. Okay, we have A, C, and D. All submissions have been rejudged. Yeah, so what are we doing wrong here? This isn't a hard problem. So I'm saying, yeah, is it ever not the most 2s in a row? We have 1, 5. Oh, no, just kidding. What if we have 1 test case, 1 thing, and it's this? Then we print 2. 1 test case, 2 things, greater, greater, 3. 1 test case, 2 things, less, less, 3. 1 test case, 2 things, greater, less, 2. Yeah, that's right. 1 test case, 3 things, greater, greater, less. So it should be 3 things. Whoa. Whoa, why is that? Oh, dang. All right, yeah. Wait, oh no, crap. I'm an idiot. That's a dumb submit. That might not even be right. Okay, because I have it in else. So we want greater, then we want count plus plus. Oh wait, no, we still want else count equals 0. So the max, how is this 1? What? We have a greater than sign. So we add 1, now it's 1. We have a greater than sign, so it's 2. So I just hope I didn't get wrong answer just because 1 there. I did. All right. Yeah, I hope I did get on to this one. All right. Problems. Good. All right. Let's do E. So we have a playoff tournament of 2 to the K teams. Yeah. So I don't know. I just wasn't resetting the variable. Oh my goodness. People, you got to write better problems. I'm sorry. Look, the first several problems, great job. Very well done. This one is a travesty. You can't have statements this long. This is not going to fly. I'm sorry. 2 to the K teams participate in a playoff tournament. They're numbered 1 or 2 to the K. Okay. In order of decreasing strength. So team 1 is the strongest and team 2 to the K is the weakest. Smaller number will always defeat a larger number. First of all, the teams are arranged in some order during a procedure called seeding. The team is assigned a unique number from 1 to 2 to the K called the seed, and that represents its starting position in the playoff. A tournament consists of 2 to the K games, and they are held as follows. The team split into pairs. Team 1 with seed 1 plays against team with seed 2. Team with seed 3 plays against team with seed 4 in this exact order. So 2 to the K teams, 2 to the K minus 1 games are played in that phase. When a team loses a game, it is eliminated. All right. After that, only 2 to the K minus 1 teams remain. If there's only one the team that remains, it's declared the champion. Otherwise, the 2 to the K minus 2 games are played. The first one of them, the winner, is seed 1 versus seed 2, then seed 3 versus seed 3, 4, and so on. Okay, we get it. After the tournament ends, so it's basically just like single elimination tournament. After the tournament ends, the teams are assigned places according to the tournament phase in which they were eliminated. In particular, the winner of the tournament gets place 1. The team eliminated in the finals gets place 2. Both teams get place 3. All those next teams get place 5, and so on. Now that we established the rules, we do a little rigging. In particular, we want team 1, not the team with seed 1, to take place 1. We want team 2 to take place 3, or take place 2. We want teams 3 and 4 to take place 3, and so on. For example, the picture describes one possible way the tournament can go with k equals 3 and the resulting teams with resulting places. Some seeds are already reserved for some teams. We are not the ones rigging the tournament, apparently. Or we're not the only ones rigging the tournament, apparently. Okay. We have to fill in the rest of the seeds with the remaining teams to achieve the desired placements. How many ways are there to do that? Okay. So, let's see. We have 1 verse 5, 2 verse 8, 3 verse 7, 4 verse 6. So what's important here is that in every pair you need a top half and a bottom half. Okay, and then you have these ones. Now here in every pair you need a top half and a bottom half. How many ways are there of doing that, and so on. Yeah, all that you care about is the number of top halves and bottom halves. The answer might be 0. Yeah, okay. It's a very easy problem, I think. So we can say this is int n equals this, fs.nextInt, int array a, fs.read array size n, and then int solve int array a. If a dot length equals, well, maybe it's a bit tricky. So yeah, let's do this in a minute. Okay. Actually, we have to do it now. So we need to split this up into and then we need to say how many ways are there to arrange the tops so that every pair has one top and one bottom. And we also need to know how many free spots are there. Do they guarantee it's possible? Can it be 0? Output is 0. Yeah. Okay. So this is going to be static long count immediate, and we'll need int array a, and then int cut point. Yeah. And then as far as which top it is, it doesn't matter. Ooh, we also can shuffle the bottoms in any order. So what is this? Just the number of ways to arrange the bottoms? I think that's just the answer here. Or 0. Cut point will be n over 2. All right, and then int array next. So well n is not equal to, oh, I guess well int size will be n, and well size not equal to 1. We'll do some stuff. Size divided by equals 2. Stuff is new a, new int array size over 2. So new a at I equals this is kind of annoying. Okay, so if they're both fixed, then so if a at I is not equal to 0, I guess we want I plus equals 2 here. and a at I plus 1 is not equal to 0, then new a at I over 2 equals math.max a at I and a at I plus 1. Else, if a at I is not equal to -1, a at I is not equal to -1, then if a at I is greater than the cutoff, okay, so times equals, so if, yeah, we can just do this here, I guess. So if this is greater than cut, then are they numbered 1 to n? Yeah, or -1. Okay. Yeah, I think 2 to the number of unfixed pairs as well. Okay. All right, then if this is bigger than cut, then new a at I over 2 equals a at I. Else new a at I over 2 I over 2 equals -1. Okay, and then we have an else if. Then we do basically the same thing. This is just +1, this is +1, and then we have else new a at I over 2 equals -1. Okay, so both fixed, one fixed, neither are fixed. Okay, and then what do we have next? So then we have size equals 2, a equals new a, cut plus equals size over 2. So first it's, let's say n is 8, first the cut is 4, and then the size is 4, and then cut is 6. Yeah. Okay. All right, and then at the end, we do out.println ans. Long 2's is 0, and then long rest equals 0. 2's equals 1, I guess we'll say. Rest equals 1. Return mul 2's rest. All right, so first, this is the impossible case. So 4, we'll just call this cut. Int I equals 0. I is less than a dot length. I plus equals 2. If a at I is not equal to -1, and a at I plus 1 not equal to -1, then if a at I is less than cut equals a at I plus 1 less than cut, then return 0. Okay. All right, so that's the impossible case. So the next one, we want the 2's. So 4 into I equals 0. We'll just do the same thing as we did here. If a at I equals -1 and a at I plus 1 is also -1. Then 2's equals multiply 2's by 2. So we can swap the order. We don't care about the order. Yeah, is that good enough? Just do that order. Yeah, because it'll get removed anyway. Okay. So next thing we have is the number of free things. So this is factorials at n free small. We can order them any way we want. We have t is 1. And we need n free small, this is an int. We could just count this here too. Nah. All right. So, what if, yeah. So we need int array, I guess array list, integer, things equals new array list. We'll say if a at I is not equal to -1, things dot add a at I. Did I get this solution to be right, by the way? Finally, okay. All right. +1, +1. Okay, so if things, oh, so now we need to see if we have anything less than cut, don't add free. So for, so have small equals false. If I is less than cut, then this isn't I, so this is J. And have small equals true. If not, have small, then n free small plus plus. Okay, and then I think we're done. Let's try it. This is problem E. 0. Y. All right, so why does this only run once? Should definitely run at least twice, right? N is 2. Okay, that's also odd. This should be 2 to the n. And next 2 out of bounds for length 2. Should be size. So why are we getting 0? So what is cut? Yeah, initially the cut's 2. Less than or equal to. Okay, let's try this one again. 0, good. This is 16. Ooh, okay, works. 768. 1. All right, let's try it. It's a pretty easy educational round so far. Maybe F is the stumper. Oh wait, did I? Yeah, that's fine. That one and then this one. Okay. Copy, paste. To problem E. Submit. Wrong. Test 8. Okay. Times equals. Ants equals 1. Multiply by this. Interesting. Wrong answer, test case 8. Yeah, how big can this get? 2 to the 19? Oh, dang it. Oh, it's my mod. Mod. So then that seems likely that's right then. If we pass 7 cases, small mods, for modding correctly, it should be right. No. Really? They should all be small, and then my factorials uses mod 2. I passed 7 cases and I get it wrong? odd. Yeah. So this can be, we need 3 or 4 here. So, well, okay, let's see. So where can the 2 be? 2 can be here or here. So that's 2 options. So I think this is 4. Yeah. So let's, yeah, I don't. Well, what should we do? Should we read F? I guess. Berlin International College has just finished. Monocarp and Polycarp, as the jury, are going to conduct an editorial. Unfortunately, the time is limited since they have to finish before the closing ceremony. There were n problems, numbered 1 to n. The editorial for the ith problem takes AI minutes. They're going to conduct an editorial for exactly k of the n problems. Okay, so just the easiest ones. They have a full problem set of n problems before them. They remove the n minus k problems without changing the order of the remaining k. Monocarp takes a prefix of them. Polycarp takes a suffix. They go to different rooms. Conduct editorials for their problems in parallels. The editorial takes as much time as the longer of the 2. Help them choose the problems and split in such a way the editorial finishes as early as possible. Print the duration of the editorial. So you can choose any k. So you just choose the k easiest ones, but maybe not necessarily. Interesting. So you brute force the split point, right? If you know what the split point is here. That's actually kind of tricky. Yeah, you could brute force the split point and then you could like binary search it maybe. But it is definitely annoying. Can we have some of the first k things in a range on a segment tree? Probably not. Not if k is big. Okay, so why am I getting E wrong? Wait, what did they say? This is something with penalties for wrong submissions? Okay, interesting. Okay. Yeah, what could I possibly be doing wrong? Could I write a brute forcer here to count? Or could it be a mod thing? So I'm not doing 10 to the 9th plus 7 anywhere. Let me make sure this one is using the right mod. Yeah, it's got to be right. Just 1 times a bunch of stuff, right? Are all of these integers valid? Yeah, all values are distinct. All values are either -1 or distinct. Okay, fine. Let's just, I mean, we can easily test this. So we can do 4 or 5 would be 32, right? That's 8. That's smaller than I had thought. Okay. So what if we do 4? Okay. And then 6. I don't know. Seems reasonable to me. Yeah, is this idea wrong? So we're saying it's true to the number of unfixed pairs times the number of cuts. Oh, times the number of ways to arrange the bottoms. Yeah, because all these things are identical. So then is this wrong? So if they're both not -1, this is the max of AI plus 1, or AI and AI plus 1. Yeah. Sure looks reasonable. Ah, crap. It's the smaller ones that win. The smaller things win. Wow. Right? 1 is the best. Dang it. So let's break this. So if we have 1, that's annoying. Okay, so 1, that'd be 2. Three. Yeah, this should. Okay, so this is 128. This is 192. This is 128. So, yeah, what's going on here? Why, when we do bigger numbers, we have more freedom? Because we arrange the smaller things more, yeah. Okay, so here we can do this. So we can just for int I equals 0 less than n plus plus if a at I equals -1. Continue. Otherwise, a at I equals n minus a at I plus 1. $128. 192. Submit, E, paste. Nice. 55. Not terrible. Solve F here. All right, so yeah, we are writing this editorial, and we need to pick K problems, K of the N problems, which takes some amount of time. And we want to do a prefix and some suffix. So one option is just pick the best K problems. And then it takes 2 minutes. Okay, yeah, it just takes 2 minutes. All right, so we're picking 3 problems, right? So 1, 3, 5, and then it takes, ooh, yeah, that's inconvenient, but I guess it'll take 6 minutes. Yeah, okay. 3, 1, 3, 5, also takes 6 minutes. Why is this any different? Oh, now it takes 4 minutes. Oh, 5 minutes, I get it, yeah. Okay, 6. Yeah, so when would you ever, first thing to figure out, when does the greedy not work? So the greedy is just like pick the smallest n problems and then solve them. And then, or like split almost evenly by time. So like let's say you have something, so you can increase the total by and also improve the distribution between the two people. Yeah, so if we have this, we can replace this big with like another big, and then that'll improve the distribution. So you could get rid of this. And you could have like bigger. And then, yeah, here maybe the split point's like this. And now the split point would be here, but instead we can move it over a couple, maybe like that. Okay, key observation though is your only, like, things you remove are either going to be directly to the left or directly to the right of this bar. Yeah, this is a bound on your answer. Whichever of these is bigger, you know your answer is smaller than that. Like the amount you can improve. Which isn't that great, but... yeah, maybe let's take this as an example. So we need to pick 6 of them. So biggest one is 20, right? So this is big. So 20 is big. Next one's 16, that's big. Next one's 14. Next one's 10. Oh, next one's 11. So now we have 1, 2, 3, 4, 5, 6 left. And this is our distribution here, I guess. So 18 and then 10, 18. So you have a 3 stuck in the middle. So it's 18 plus 3 is 21. You can't do better. Okay, well, can we have an example where greedy doesn't work? One example, please. Okay, so now we pick 5. Okay, fine. So biggest one is 19. Next biggest one is 15. Next biggest one, 13, I guess. Then 13. So now we have 6 things. Remove the 12. Okay. This is still gonna work. 9 plus, so 15? Is the answer 15? It's 18. Ah, because 9 plus 9. Yeah, that's not helpful. This is incredibly unhelpful. All right. Let's do it ourselves. Ah, okay. So this will increase our total by quite a bit. Like, do we replace 2 of them ever? It does, yeah, so this increases total by a lot. Maybe not a lot. Yeah, I guess the more extreme cases are when everything is basically the same. So we feel like 4, 4, 4. Well, no. 4, 4, 4, 4. Okay. Yeah, but what if it's like 10, 10? And then we have an 11 here. So you have 4, 10. Ah, this. Yes, that's a case. So we have 4, 10, 4. So this is 14. But instead we can do just 11 and 2 4s. But again, it's something in the middle. So, yeah, is it always... we'd only want to remove something in the middle. I think we even only want to remove one thing. This is a really sketchy though. I could just try it and see what happens. I guess, could I write it? How much time do I have? I have the luxury of time. So could I just write a brute forcer here and see? What does the brute forcer entail? So this would be, we pick, how many things? We pick k of n things, brute force, and then just like trial distributions. Okay, that shouldn't be that hard. This is multi-desk case, so we have int n equals this, k equals this, int array a, fs dot read array n, and then we'll have long solve, int array a, int k. Okay, and then static long solve int array sub, or I guess we'll have an array list, integer sub, long ans equals 0, long sum equals 0 for int I and sub, sum plus equals I. This equals math.min of ants and math.max of sum 2, or sum minus sum 2. And we need to do this twice, I guess. And then sum 2 plus equals I. And then out.println. Actually, we only need to do it once. And we'll say sum 2 equals int ants equals sum. k, and then we need for int mask equals 0, mask less than 2 to the n, mask plus plus, if integer dot bit count of mask is not equal to k, then continue. Otherwise, array list integer keep equal, or sub, I guess, equals new array list, and then we'll say for 0 less than n plus plus if sub dot contain, or if mask and 2 to the I is not equal to 0, sub dot add a at I. Okay, and then ants equals math.min of ants, or solve sub. Okay. Does this work? 2, 6, 5, 21, 18, 1. All right. Awesome. So we've got a brute forcer, so we can compare this now. Let's actually take all of this into the real solution. And we just need the function signature here. So our hypothesis is we are going to consider just doing this. Remove something in the middle and replacing it with one other random thing that we don't previously pick. Okay, first we'll have a pair array pairs, new pair array n for diagonal 0 less than n plus plus, pairs at I equals new pair of I a at I, and we'll arrays dot sort the pairs, and then we want the first k. So, but first we gotta, well, yeah, I guess we can just keep them in order. kept equals pairs, or kept at I equals pairs at I, and then arrays dot sort kept by AB to integer dot compare A dot index to B dot index. All right. So now we have them sorted. All right, so how yeah, now we need to stop and think. So like how are we actually going to check replacing anything with anything else? So let's say we have the in a bit, I guess we can binary search the split point. Yeah. And that'll give us, we could do this with prefix sums even. So this will give us an n log squared solution. This is n times log squared. But if we TLE and know it's correct, we could make it n times log n with prefix sums, because it's almost prefix sums except for the one thing. Yeah, okay. Let's get the or the bit. Come on, what's going on? Continue. Please don't leak my phone numbers and stuff. We want a bit. There we go. We'll get a static class bit. This has to be a long here. New long array. This will be long read, long sum, long value, long query. Okay. All right. Yeah. So. Okay. So now we're gonna need static solve2 of a bit. Solve with binary search. Yeah, all right. I have to go to the bathroom, but I think we're getting closer to a solution that might just be wrong. So one of the trickiest parts here is I have absolutely no reason to think this would be right, other than just like blind intuition. So I don't know how I feel about that, but might as well give it a shot. It doesn't even feel right, to be honest. That's kind of the biggest problem. Yeah, okay. Well, let's do it anyway. So we'll just say sum plus equals p dot value. So now we have the sum of everything. And then split 0 for, okay, I guess we want long best will be sum for int I equals 0 less than kept dot length I plus plus. I'm at that max of long prefix sum equals 0 plus equals kept I dot value prefix sum or sum minus prefix sum. Okay. Excuse me. Okay, yeah, so now for int I equals 0, we need this bit here. Okay, so we have this. And then we can say if in kept at I continue, otherwise, this is replace the thing after. What if it's 1? Yeah, so now it won't be 1 for sure. These all have to be at least 1. Yeah, so we're good. So this replaces the thing after. I guess the thing before. So what is split? This is kept at split minus 1. Dot index. Dot value. This bit. Okay, and then we'll say return ants, and then ants equals math.min of ants and this, and we're good. All right, so now for this, we need long best equals, we should also take the n here, int n, long best equals bit.sum, or bit.query from 0 to n minus 1, turn best. Okay, and then we'll say int l equals 0, r equals n minus 1, while l is less than or equal to r. Int mid equals l plus r over 2. Static long eval at long mid. I guess int mid. And then int n, and then bit. This will be return bit dot, or return math dot max. Ooh, that's not gonna work. All right, so long left val equals bit dot query from L to mid. And then long right val equals bit dot query from mid plus 1 to n minus 1. This is actually 0 to mid. So we can say best equals math.min best, or math.max of left val or right val. And then we can say if left val is less than right val. So if left val is too small, oh wait, if left value is too small, then make it bigger. Yeah. Does it work? Okay, let's see. So first of all, 2. Nice. Six doesn't crash. That's honestly more impressive than what I was expecting. Okay. Next, we have this case. That's it. Huh? Ah, 4, 3, right? 4, 3, we pick 3 things. $11. Yeah, okay. I broke it. All right. So, let's see. So let's make a toString here. Public string toString. All right, and let's print what we keep. So 4, 10, 4. So that's right. Okay, so that's good. Okay. So now we want to try replacing it with something. All right, so -0. So this is where we're going wrong. Okay, so best. So it returns 14, but that's not right. Okay, all right. So sys out. So at 1, we get 10, 14. I thought we got rid of this. Ah, wait a minute. Ah, thing before I, but also thing after I. But also, that's not right. Because this shouldn't be 4. Oh, it is 14. Yeah, that's right. Okay, so now we need this, and then we need I plus 1. Ah. So split, 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 split. $11. That's right, isn't it? It is right. Okay, let's just say static final boolean debug equals true. Replace all. And we should be good. Let's run this one more time. So now the question is it remotely right? That's returning. db equals false. Dang it. Okay, so this is probably hopeless. But now that we have a brute force, we can maybe find a case where it's not. All right, so yeah, let's get the brute forcer here. Okay, so we have these. We also need to generate an array. So we can do this. We can say n equals 10 and k equals 4. And then int array a, new int array n. Okay, so we have this. All right, nk this array, and then yeah, so if ant's not equal to bf, ant's throw null. Got one. Okay, so sys out a plus, or I guess array is typed. Okay, and then let's try making this like 6. Okay, let's make this 10. 5. Next -1. Huh? +1. 4 and 3. 4 and 2. Okay, so we need 4 and 5. All right, I say 9, BF says 8. I need to pick 4 things. You can do 8 and 8. Yeah, that's pretty easy. That's, I guess it is somewhat concerning. Okay. How much time do we have? 15 minutes. I should have copied my original solution. Okay, oh well. Yeah, let's actually get a copy of it. Copy, so this is f sub.java. Okay, and then we want this. So I say 9. The answer is okay. So debug equals true. What's wrong with this? It's not a duplicate field. What are you talking about? Okay. So what are we thinking here? So time to replace index 3. Can we get these smaller? Can we make these like 1, 1, 1, 2, 2? What happens here? Yeah, what if we do 1, 2, 2, 3, 3? Now you can do it in 4. Returning 4? What the heck? You're telling me when I subtract 2 from every number, it works? How the heck does that happen? Five, 4, 4, 5, 3. What? It works? How does this happen? That's bizarre. So binary search does different things. So 2, left val, right val. Okay, let's see. So let's just do this the easy way. Need a marker. So we have 5, 4. This is an easy case to debug. 4, 5, 3. Anybody can do this. So this is, we keep index 0, index, oh, crap. Yeah. Well, this breaks the idea. Okay. So we're totally wrong. So, yeah, back to the drawing board. This is a good case, though. Let's say you knew the dividing point. Then you would just want the minimum this number of things on this side and this number on this side. Is that binary searchable? Oh, is this really that easy of a problem? Dang. Yeah, it might be. Right? If we can binary search it. because it's, yeah, we binary search when they become equal. They're monotonic. So you can do it with a treep. I should have gotten this. Oh, I played too risky. I played way too risky. It's not a hard problem. I also should have seen that by the number of people solving it. Yeah, you can do this just with like any data structure. You can just brute force the middle point. If you know the split, you want the cheapest things on the left, cheapest thing it's on the right. Dang. That was stupid. Well, good thing it wasn't rated. Yeah, so you can, so I guess let's make sure we have this right. You could have like a treep of what's on left, treep on left, and then treep on right. And your ops are move one over, move one thing over. Yep, so it's just delete from one treep, add to the next treep. Those are both log n. And then it's like find the sum. Oh yeah, find the sum of the first k things. Sum of first k things. That's in log n. We've log squared solution. Dang it! Yeah, alright. That's annoying. Should have gotten it. Use treeps. The left treep. Remove element from right treep. And get the sum of the first k things in a treep, each in log n. And then we just n times do that, and then binary search the split point. That's the solution. Just to mark my territory here. People TLEing. Ah. TLE might be a problem. So yeah, could we speed it up? I don't know, these might be like silly solutions though. Are the good people TLEing? They are. So I wonder if n log squared is too slow. That solution makes a lot of sense though, nevertheless. Oh, look how quick. Speedy. Yeah. All right. I guess that's my solution. Yeah, we can talk about the solution ideas here. I don't have time to code it, but talk about solution ideas. Let's get rid of everything. All right, so solution for A is you either can always do it in one jump or always do it in two jumps. If you can do it in one jump, obviously you do. But otherwise, you know that, like, if you can't do it in one jump, then certainly x is divisible by k. That means if you take a step of size 1 and then you take a step of size x minus 1, neither of those are divisible by x, or by k, sorry. Because if k is like 3, for instance, that's, let's say x is 12, then you know 1 isn't divisible by 3, because k is 3 is at least 2. And you know 11 isn't divisible by 3, because 12 is, and if you subtract 1, you'd have to subtract 3 to get to the next thing that's divisible by 3. So 1 is not enough. So yeah, you can just do 1 and then x minus 1. That'll work. Yeah, so that's the solution to A. Awesome. For B, this one is not too bad. Basically, you just need to count the longest continuous range of greater than or less than in a row, and it's that plus 1. That's the idea. I don't have like a super solid proof, but it's pretty intuitive that like that's what's constraining you. And you can just use the numbers like 1 to n for that. And anytime you have like a decreasing range, you have it, for decreasing range, you have it end at 1, and then increasing ones end at n, and so on. So yeah, it's just the biggest number of continuous greater thans or less thans in a row. And that's your solution to problem B. All right, problem C. Yeah, what one was this one? We have zeros, ones, and question marks, and then it's, oh yeah, this one's even easier. So yeah, anybody can do this one. So you want to minimize the number of range reversals you need to sort this. And the observation here is that if you are sorting things by range reversals, what's going to matter is when you have borders between zeros and ones. So that's when it could cause a problem. Basically, what you're going to need to do if you sort this is first you're going to need to get all of the ones together. And once you have all of the ones together, you're going to need to put them at the end, right? So you can do that with just one operation. You take the beginning of the group of ones to the last element, you flip that, and then all the ones are at the end. So the part that's difficult in this sorting method that you have to do is getting the ones together. Well, we can do this by just minimizing the number of blocks of ones and not creating any extraneous blocks of ones. And if we do that, then we'll be fine. So yeah, the idea here is just we will keep everything the same as what they are on the borders. So basically, if you have two ones, you want to keep this, like in this case, we have a 1 on both sides. So we have to make sure these stay ones. Otherwise, we'll increase the difficulty of sorting. In this one, it has nothing on this border, a 0 on the left border, so you want to keep it as 0. The easier way to implement this is it's equivalent. Oh, in this case, if you have a 0 on one side and 1 on the other, it doesn't really matter. You just want to make these all the same thing. So the easiest way to implement this, in my opinion, is just set this to whatever the thing on the left is. And then if there is nothing on the left, like in this case, then set it to the thing on the right. So yeah, my code for that is quite simple. Oh, here's the code for A, by the way. Pretty straightforward. 2 cases. For B, I did this. Yeah, this is a complicated way of doing it, but this works. Yeah, so I just find the first thing that isn't a question mark with a for loop. And once I have the first thing that's not a question mark, I just set everything either equal to the first thing that's not a question mark, or I update the thing I'm setting things to whatever the last thing was if I see something that isn't a question mark. So that's C. Pretty easy. Makes sense. Awesome. D, we got this bracket coloring thing. Yeah, so for this one, basically the classic observation here is the following. When you have balanced bracket sequences, it's almost always useful to think about mountains. So what do I mean when I say that? If you have an open parenthesis, think about you have a total, which is how many things you've seen, right? So if you have open close, that's this. So here your total is 0, then your total is 1, and then your total is 0 again, of how many unmatched open parentheses you have. And then if you graph this, then this is the total, right? So it starts at 0, and then it goes up to 1, and then it goes down to 0. So yeah, basically, so we're going to imagine these mountains here. And if a mountain ends at 0 where it starts, then it's valid, unless you have any of these valleys, right? So if it goes like this, that corresponds to open, close, close, open. And this is not a normal balanced bracket sequence because you're not allowed to like have a close before you have its open, which is what happens here. And that corresponds to having a prefix sum that has more closes than opens. So if we consider the mountains, and this is the ground point, what we can do in this problem is we can split it anytime we hit the ground, right? And we're allowed to have valleys, but the valleys just can't have any mountains inside of them. So if we split it every time we have one of these, right? And you have, maybe you do something like this, blah, blah, blah. Let's give us some more space to make it more interesting. Go down, go up, go down, down, like this. If we split it like this, we can make this one color 1, this color 2, and this color 1 again. And now if you combine these, like if you imagine getting rid of this part, and you just go from here directly to this, then this part is all positive, right? So this all together could be all one mountain, and this can all be one mountain that's negative. So that's the idea. Anytime you hit 0, you start a new group, and then you make all of the ones that can be positive, you make all of those color 1, and you make all these color 2. So either it's possible to do immediately, or it's not. And if it's possible to do immediately, then you're just done. If it's not possible to do immediately, you can always do it in 2 colors. And then obviously you can't do better than that, right? So that's a good enough solution for us. Yeah, and there you go. Let me clean this up a bit. Yeah, so that's the idea. I don't even use this. Okay. Cool. So that's the idea. So we check if the total is positive or negative. If it is only one of them, then we can do it in 1 color. Otherwise, we need 2 colors. And yeah, this is how I keep the groups together of like where it's above the water level or below the water level. Awesome. Yeah, that's D. Talk about E and F too real quick. So E is actually pretty easy. You just have to be careful with your counting and make sure you read the question correctly, which is the part that I messed up. Yeah, so TLDR, you need things to happen like this. So you need team 1 to get place 1, team 2 to be place 2, and so on. And you might not have determined which people are which spots here, which seeds the problem calls them. So to do that, what you have to notice is that in the first group, for every pair, you need 1 team to be in the top half and 1 team to be in the bottom half of the 8 people. So you need 1 that's 1, 2, 3, or 4, and 1 that's 5 through 8. We have a top half, bottom half, top half, bottom half, top half, and top, bottom. And we have this in the first group. And the nice part about the way these tournaments are structured is that every round works the same way. So we have a top half and bottom half here. We have the same thing here, actually, except the numbers are just half as big. And we have the same thing here. The numbers are just half as big, and there are half as many people, and so on. So we did the same thing every time, which means the coding for this is actually really easy. We just do it recursively and just keep calling the same method. So yeah, that'll give us the idea. But how do we count how many ways there are to do this? Well, the freedom we have at an individual level is everyone who gets eliminated, we don't really care which of them has which team number. You can swap teams right here. So teams 5 through 8 are getting eliminated. So you can swap teams 5 and team 7 and no one else will care, right? Because from here on, from this round on, all of those teams are indistinguishable. Teams 5, 6, 7, 8. So you have like however many, let's say team 8 is fixed, but team 6, 5, and 7, all of those can be swapped between each other. They're all -1s. Then you have 3 factorial ways of ordering those. And then additionally, if teams 1 and team 5, if neither of those are fixed, then for this pair, it could either be 5, 1 or it could be 1, 5. So we have to multiply by 2 to the power of the number of unfixed pairs we have here. And then once we've done that, we know like the set of teams that will make it on, right? Because we know the teams that make it on, it has to be teams 1, 2, 3, and 4. Otherwise, we did something wrong. And we're only counting the ways that 1, 2, 3, and 4 make it on. We don't know which of these are ones necessarily if one spot wasn't fixed, but we know which teams are going to make it there. And we know which ones are tops and which ones are bottoms. So we know all of these are in the top half. We also know if let's say team 4 was fixed to be here, we know team 4 will be in this spot. So it's the exact same version of the original problem, but just with half as many teams. And we have to just calculate which teams will make it onto the next level. So yeah, the cut bar will like drop in half. My code is not super readable because I misread the problem. I thought the teams with bigger numbers would pass, but really it's teams with smaller numbers. But basically, this part is what counts the solution. And I count a couple things here. First, I count, do you ever have a pair of two people that play each other, but they're both either in the top half or in the bottom half? If that happens, it's impossible. If that doesn't happen, the two things we need to count are how many pairs of twos are there where the twos can be swapped, and also how many things that I call them small, I call them n-free small, but really it's like how many things are there that'll get killed in this round where we can do that number factorial of ways of ordering them. So if there are 3 things, they can be in any order. So it's 3 times 2 times 1 way of ordering those 3 things. So that's what this part does. And I won't explain the code, but yeah, that's what's going on. The other thing you have to keep in mind is like, how do you move from having n people to having n over 2 people? And that's what this is doing. So this converts the problem into a smaller version of the same problem. Basically, there are only a couple cases. If both of them are -1, then you can just, if they're both -1, you just put a -1 there because you haven't decided who's going to be there yet. If one of them is -1 and one isn't, then the one that isn't -1, if it's too small, like if that one is the one that loses this round, then you have a -1. You have an undecided winner. But if that one wins this round, that guy's the one who's going to be in that spot. And then if you have 2 people and you know both of them, you know one of them has to be in the half that wins, one has to be in the half that loses. So the one that's in the half that wins is the one that moves on. Yeah. Now, if you just copy this, it's going to be very confusing because I do mat.max, right, for the winner. Really, the winner is the min, but I flip everything in the beginning because I did it wrong. So yeah, that's what's going on here. You can definitely clean up the code a bit more. All right, last one is problem F. Let's talk about it. Problem F, here we go. Editorial for 2. Yeah, so this one is actually quite easy. I went down a rabbit hole here with a solution that's just totally wrong. But the right solution is not that difficult to come up with. I just should have thought more before ruining my chances. The idea is, let's just brute force the split point in the middle. So yeah, I won't explain the problem, but if you know the split point in the middle, then you can say, all right, what's the best way of doing the split point? And basically, we're going to pick the smallest set of things on the left and the right so that we have k of them. And we need to brute force... oh, wait. Hang on. Is this even legit? Let me think for a minute. My solution idea might be totally wrong. Yeah. It's easy. Okay. So the idea here is we are going to keep a treep. We're going to keep a set of the numbers left of our split point and right of our split point. So we'll have these 2 sets. And we need to know the solution that I'm getting to is we're just going to use treeps to do all this. But here's how. So we keep what's in the left, what's in the right half. And then what we need to know is if we take the first so many things in the left, so if we take the first 10 things in the left, what is the sum of those things? And if we take the first 12 things in the right, what's the sum of those things? We can store those things in a sorted set in a treep. So the treep will be sorted from left to right by value of things in that group. So you'll have everything sorted by value, and you can remove an instance of something and you can get a prefix sum. Those are the 2 things you can do. And yeah, we can binary search the solution we're looking for. So this will be n log squared will be the solution, which I think should be fast enough. We can yeah, it should be fast enough. You might have to do some optimization here. That's 1.2 seconds in theory, but you might have to do some optimization. A nice thing you can see is that like you can probably memoize a lot of these things, but maybe not. I don't know. Maybe it's tough. I think if you have fast enough treep code, it should be fine. And maybe you can use a bit somehow if you don't like that. I'm not 100% sure, to be honest, but yeah, that's an n log squared solution that works. And based on the time limit, it seems like n log squared is what they're going for. So, yeah, binary search and data structures. That's exactly what I was suggesting. Treep and binary search. All right. That's the solution to all the problems here. I didn't solve all of them, but I thought it was a very good contest. Except for problem E. They need to reword problem E so that it's much shorter. But I thought, yeah, other than the wording of problem E, I thought it was great. And I guess fix your samples for B. But yeah, good contest. I like it. Thanks very much to the authors. And I'll see you at North American Championships if you're coming there. All right, have a great day. That's all from me. Bye-bye.